It's a beautiful day here in Mahwah, New Jersey. The sun is shining, the birds are singing, but inside one student is not having a nice day at all.
Sigh.
What's wrong there, Ainsley?
It's these calculus problems on integration. I just can't figure 'em out.
Well, did you try a trigonometric identity? Did you try U substitution? And they didn't work?
They didn't work.
Well, did you try trigonometric substitution?
What's trigonometric substitution?
Well, I'll tell you. New from the gods of calculus, it's trigonometric substitution. When you have an integration problem that involves a radical, no longer do you have to attempt U sub or try to rationalize the function. If your problem takes any of these three forms, all you have to do is use trigonometric substitution. It helps you get rid of the radical by relying on your old knowledge of trigonometric identities. Just ask these customers what they think of trigonometric substitution.
Oh, trigonometric substitution? Of course I use it. I use it, my kids use it, I use it all the time. Like, morning, night, it doesn't matter. I think everyone should use it. I mean, it's really great.
Of course I use trigonometric substitution. It's like changed my entire life. And if you've got a problem with that, just like take a look at my 95 in AP Calc BC.
Why, of course I use trigonometric substitution. I think it's the grandest thing. Real positive and real good for the community at large.
How does it work? If the expression under the integral takes the form a squared minus x squared, then plugging in a sine theta for x will cause the expression to equal a times cosine theta squared. If the expression is a squared plus x squared, then if x equals a tangent theta, the expression will equal a times secant theta squared. If the expression is x squared minus a squared, then substituting a secant theta for x will allow the expression to equal a times tangent theta squared. These will then remove the radical to help you go on integrating as normal. Problem 1. The first step of any of these trigonometric substitution problems is to draw the triangle that you will be using. In this case, you want one of the sides to be the radical expression that is in your equation. So it is the square root of 9 minus x squared. Using the Pythagorean theorem, the other sides of this are 3 and x because this is a right triangle. You discover that theta is one of the angles adjacent to the side with the radical that isn't your 90-degree angle. And once you've found this, you can find all sorts of trigonometric equations and the equivalents, such as sine theta, which is going to be used in this. Sine theta is being used in this because the radical is taking the form of a squared minus x squared, which means that you use x equals a sine theta. And in this case, if you look at your triangle, you'll discover that a is going to be equal to 3. So x equals 3 sine theta. With that, you can find out the derivative for the x. So dx is 3 cosine theta d theta. You also are going to want to write down some of the important things here. So using this trigonometric identity, you'll discover that the radical expression is equivalent to 3 cosine theta, and that x squared is equal to 9 sine squared theta. And then the next step is to plug all of this into the equation. So first, start by rewriting your equation just so you can see it and work with it more easily. So just rewrite your expression and then start plugging things in. So for dx, you have 3 cosine theta d theta. X squared is 9 sine squared theta. And then the radical expression is 3 cosine theta. Now you can cancel out those 3 cosine thetas, and you can eventually get 1/9, you can pull that out of the expression, and you'll end up with the integral of d theta over sine squared theta. And then you can just start integrating from there, because that's the equivalent of cosecant squared theta, d theta. Then you just need to integrate from there. The integral equals negative 1/9 of cotangent theta plus c, which is also equal to negative 1/9 of that, which is the square root of 9 minus x squared divided by x plus c, and which is also equal to the negative square root of 9 minus x squared over 9x plus c. This last step is not really necessary. It's called back substitution, and is just in case you want to rewrite your expression with x's instead of thetas. Problem 2. Once again, you're going to want to start by drawing a triangle. The hypotenuse is going to be the square root of x squared plus 1, and the other sides are going to be x and 1. Now, this expression is a little different because the bottom is not radical, but instead is raised to the third halves. So instead, just rewrite it as the square root but raised to the third. This is just going to make it easier. A is 1, and u is going to be x, which is also going to be tangent of theta, because the expression is x squared plus a squared. Dx is going to be secant squared theta, d theta. The square root of x squared plus 1 is going to be equal to secant theta by the trigonometric substitution properties that we just learned. Rewriting the expression, again, just to make it easier to look at. Then you can start plugging everything in properly. So I just rewrote it twice. That's okay. That's also important. Always rewrite it twice. So now you can start plugging it in. Begin with dx being secant squared theta, d theta, and then with the radical expression being secant theta, when you raise it to the third, it's secant third theta. You can cancel these out and get d theta over secant theta because they get canceled out. Now this is pretty easy to simplify. This is just cosine theta, d theta. And now that this is really simple, all you have to do is just integrate it properly. It means that it is going to be sine theta plus c. Once again, you can back substitute into the problem to get from a sine theta plus c to an expression with x's. By looking at the triangles, you can see that sine theta is equivalent to x over the square root of x squared plus 1 plus c, and this is your final answer.
Gee, disembodied voice, that was really useful. Thanks a lot.
You're welcome, Ainsley. Goodbye now.
Chihuahua. Yeah.